Because after this double physics, I have double physics with intake 2.
Then
Then I'm having my lunch.
then
Then I have business maths.
then
Then it's 4 o'clock. At which point Sylvia will be likely gone. It'll be very difficult to hand in your report to Sylvia when she can't sign for it.
It'll be impossible.
Well, I suppose if you track her down, go to her home.
oh, I know her home.
Yeah, so it would. So exactly. So it's not impossible, KJ. Just very difficult.
She'll sue you for harassment.
Yeah, actually.
Last day she said just leave the house. Like
Yes.
just do it. I started to talk about the text. She said just leave.
Nice, nice. Yes. So if I had, you need to be thinking about getting this done before 4 o'clock, because if it's handed in tomorrow, then it'll be 20% reduced.
Really?
It's already 10% reduced. Although that's not a bad thing, because I feel like you will make up by more than 10% by fixing it.
Yes.
There's only one thing is wrong now.
Exactly.
The why.
Exactly. You're getting closer to the correct answer.
But the formula is right.
No, the formula can't not be right. You see, you've taught many times the formula's right and you were doing something wrong. So adjust your brain. The formula may not be right. Something could be wrong in it.
Should go like from check from my own laws.
Exactly. Right, Hooke's law. KJ, did you write this down? Hooke's law.
The elasticity thing.
That's right, the elasticity thing. Yeah? You dig that?
Yes.
Right. So, KJ, there's no reason for you to be using your phone unless you're looking for trouble. Looking for trouble?
No.
Right, sorry, I can't quite hear you. Say that again?
No.
That's good. Now, the more you pull on a spring, the more it pulls back. You know this. The more you pull, the more it pulls back. And there's nothing surprising there. This is perfectly normal. And in fact, we have a way of calculating how much force the spring will offer. And it's called Hooke's law. And Hooke's law says that the force which is offered when you extend by a distance x is proportional to that distance. In other words, Hooke said the force is equal to minus kx, where x is the extension, and k is some constant for the spring. So really it's the formula that's critical here, but write down any keywords you might need too. Yes?
V square minus u square over 2s.
Sounds right for the a. Do you have brackets around the v squared and minus u squared?
Yeah.
Okay, good. They're in meters per second.
Yeah.
Do you have brackets around the two
And
s?
upside the down. Yeah.
Up and down.
Yeah.
Okay, that sounds alright. What values are you getting for a?
It's like 2.5 into
Sorry, I
times
stuck
5
into.
times
Yeah, 2.5 times
5.
for the a. Give me the
Yeah.
number.
Yeah.
2.5 times 5.
Like 10 powers to 5.
10 power 5.
Yeah.
Now just pause for a moment. Was it accelerating that fast? I mean, 10 to the 3 is kilometers per hour. So you're saying you're trying to accelerate at 250 kilometers per second? No. What? Hey. What's your value for u?
U?
Yeah.
The average one or
No.
the U1?
The u1.
U1 in meters per second 0.0039.
0.0039. Sounds believable for the first one. And the v?
V 0.0043.
Also believable. And the, so hold up there. So give me the v again.
0043.
0.43 and the u?
0.0039.
And the F is 30, isn't it?
0.3.
Yeah. So, that is a tiny acceleration. What did you get for the acceleration?
Giving me E, 11,000. So 0.00, like 4 zeros
Yeah.
and 205.
205.
Yeah.
205. I got here 546. 10 to the minus 6.
Because then we got two values for U.
Yes. Did you give me the value of U in your
U1.
formula? Yeah. No.
It said U, you said no, U1.
Yeah, the first reader. Okay.
So I gave you the first reading. Because we have two readings, then we take average of both.
Okay, fine. That's what you mean by average. Fine. So
Yeah.
what is the average first reading for the
U?
U?
So 0.
Now, you know what? Let's make it more interesting because this number is small. What is the average last reading for U?
Last reading.
Yes.
Last reading is 0.01125.
And the average last reading for V?
0.01.
Wait a second. Wait. 0. Yep.
1855.
0.01855.
Yeah.
That's too small. Your mistake is what you're using your V is. You must have copied the data wrong. The speed can't be that small for the last run.
Speed was in cent.
The speed
Yeah.
on the light gauge was in
Yeah.
meters per second. Your speeds are too small. You thought they were centimeters per second, did you?
Yeah.
Why did you think that? It said meter per second on the light gauge.
Yeah, no, it said it's in centimeters.
Where did you notice?
In some paper when I was doing a trial and changing.
It was meters per second, for sure.
Well, I did this, so I don't have to change the speed.
No, the values you wrote down are the speeds in meters per second. But this is the problem too. Alright, you have this KJ attacking? Yes? Okay, so let's have a look at the units for K. So, if you have F equals minus KX, then K will equal minus F over X. So you can see that the units of K would be newtons per meter.
K is a constant.
Oh, yes. Called the spring constant or the stiffness constant. Okay,
Will they ever call it Hooke's constant?
sure. Why not? Right. Some more definitions. The natural length L of a material is the length at which the material tends to return to. It's the length before any extending force is applied. That is, it's the length it wants to be at. So in other words, the rest length.
What if you pull the material and it doesn't go back?
Yes, we'll get to that. Got it? Talking?
Oh, not good.
Yes? Talking? No?
Almost done.
Got it? Okay. And the extension of a material is the length at which the material is extended beyond its natural length. That is, it's the x. So the x is often called the extension. And in fact, some formula books would use e instead of x, which I don't particularly like. Yes? Got that? Yep. Right. Oh man, that graph ain't right. Yeah, this graph is way too big. It's half that size. One moment as we recompile. Success. Where are materials? Hooke's law. Alright, let's resume. We were at a graph. Natural length, extension, and kablami. Right, so what we got here, on the x-axis is the extension, and on the y-axis is the force. Or maybe to be more precise, it's the absolute value of the force. The force is usually taken to be negative because it will go in the opposite direction. But of course, if we just change our axis the other way around, we can make it plus. So the sign is not actually important. But what is important is the shape, and it's not surprising that it's a straight line, because if you look at the formula, well, here it is right here. If you're going to put this on the y-axis and the x on the x-axis, you can see exactly what the slope is. Now, actually, what I really did was I put minus f on the y-axis. In other words, I made the force a positive number. Anyways, you can see clearly, I hope, that the slope of this line is what? No, it's not a trick question. The slope of this line is
1.
oh, dude.
6.
No. And you're not even listening, so don't you answer.
Minus
It's
k.
6 times 10.
Minus k.
Not quite, KJ. This is on the y. This is on the x. So this piece here,
K.
so what is the value of this gradient, the slope?
K.
You said minus k. Right, so the slope is the k. We figured that out using our superior knowledge of graphs. Let's figure out what the area represents. Right, so if you look here, Here is F, and here is 0, and here is 0, and here's K. So in this graph here, we started off with no extension, and we increased the extension to a maximum F max. So we started here, and we increased the extension until we reached some maximum. Now what's the units here? Well, it's area. So the units will be this unit multiplied by this unit, which is newtons multiplied by, meters multiplied by newtons, or in other words, newtons multiplied by meters. But what's newtons multiplied by meters?
Newton meter.
Yes, correct. Newton multiplied by meter is Newton meter. Thank you, KJ. And Newton meter is?
With energy.
I would hope so. Comes from semester 1 mechanics.
Is
Tick, 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 tick.
cosine distance.
Which is?
Moment.
True, but not here. Joule.
Yeah.
Remember, work is force by distance.
Yeah.
So if this area is in joules, what do you think it could be represented?
Energy.
Yeah, and work.
To pull.
Exactly. So the work required to pull the spring from a 0 to an X is this area, which will be a half the base by the height, but you know what the force is from Hooke's law. So that's a half, the force is kx, so it's a half kx squared, basically. That is the formula for the work required, the work done when a spring is extended a distance x from its natural length. So you can see that if the k constant is bigger, more work is required. A small k constant means the spring requires less work to be extended. Okay, you got that? Right. Now, that's what we imagine the graph looks like, but in the real world that's not what it looks like. In the real world it looks like this. So the graph is straight. However, when it is extended too far, it's no longer linear. So this point at which it breaks is called the elastic limit. This is when the graph starts to become a curve. Now, I will give you an example. If you had a spring, and do you think it will follow Hooke's law? Well, of course it will, it's a spring. But will it follow it forever? No, because if you pull the spring long enough, what will happen with the coils? It will start to unravel until all you're left with is a long metal wire. Right? So at some point, there's a limit to how much you can stretch a stretchy material until it no longer stretches back. This is called the elastic limit. They often ask you to draw this graph in the exam, and there's two parts of the graph which aren't named here. Yes? There's this part here where it follows Hooke's law, and there's this part here where it does not follow Hooke's law. I'll give you the names for those in a moment, but when you draw this graph, please leave some space to write the names for this part of the graph and this part of the graph. Leave a space to write the name. So they often ask you to draw this in the exam. So a quick sketch, please. Yes? Dude, don't you want to do your physics class instead of your lab reports? And don't you think, it's kind of uncool in the middle of a physics class to ask for help for your lab report that was due 1 hour and 5 minutes ago? Bit uncool?
7 minutes ago.
1 hour and 7 minutes ago. Yes, what's your question?
The only thing, all values looks fine now.
Yes.
Thanks to you. But the percentage of Y, it's around 49%.
The percentage of what?
Y.
What percentage?
Percentage of force.
Percentage of force?
Yep.
What are you talking about? Why are you calculating percentage?
I watched the video, it's a good thing to do the percentage correct.
Ah, percentage of y?
Yeah.
Or percentage of slope? I mean, the percentage error. Is that what you're trying to do?
Yeah.
Yeah, so that's on the mass, not the y. Yeah,
On the mass.
on the mass. So you estimate the mass from the slope and compare it to the true value of the mass. You can get a percentage error on that.
So
What's your value of slope? What's your value of slope?
slope 0.8218. 8218.
0.8218.
Yeah.
Now, what was the mass for your whole system? Trolley plus weights.
1 in kg?
Yep.
1.05.
Yeah, okay, so you have a 14% error, which is pretty big, but you know, that's life, these things happen. What's your R squared?
R squared 0.9819.
98?
Yeah.
Then your M should be better.
This is correlation, this
Yeah.
is program.
Well, hang on. The R squared, no, oh yeah, no, 0.99. That's quite good. So your slope is 0.82. Are you sure your total mass is 1.05?
Yeah, because trolley was 600 and total was 450 now. Down
How much was the trolley?
600.
You sure it was that much?
Yeah.
Okay, and how much was all the weight on the trolley?
450.
You only used 450?
Yeah, you said 1.05.
Okay. Yeah, 1.05. So, possible cause for error is that your S wasn't quite 30 centimeters.
Yes.
What did you get for your mass?
Horrible.
What?
My seventh experiment
Ne-
was horrible.
What did you get for your mass from the slope? You're looking at me like I'm a crazy person. What did you get for the value of the mass estimated from the slope? Or you didn't do this?
I didn't.
He just submitted because he don't want to do it.
There was no
He don't
time.
want to do it.
I usually
Did
want
you
to.
even calculate slope?
Yes.
What did you get for the slope?
0.13
Yes?
something.
No, you didn't get 0.13 something, did you?
No,
Did
it was
you?
7 point something.
There's a big difference between a 7 and a 1. My goodness. The value of the slope you should have been getting should have been around about 0.95. This would give you a total mass of 1.05 kilograms. So your slope, Fahad, is what is it? 0.88, 0.82?
Yeah.
It sounds like your slope is too small. But anyway, it doesn't matter. It doesn't matter. What did you get for your uncertainty for the slope?
For the slope,
Yeah.
35x and 35y. UOM 0.36.
0.36?
Yeah.
And what did you say your slope was?
0.8218. 540.
So again, sorry, 0.82.
21.
Yeah, and your uncertainty was 0.36, was it?
Yeah.
Right, so that means your estimate of the mass is within the uncertainty. So that is cool. Alright.
Good.
It's alright. It's alright.
It's all.
Your values are not.
So wrong.
No, I mean, the value of the mass and the uncertainty and the true value of mass, the, the important thing is that the true mass value is within the uncertainty of the estimated mass. So you estimated your mass at something like 1.4, but your uncertainty was plus or minus 0.36, so the true value is within the uncertainty. It's like saying that the resistance in the resistor was 1.1 ohm plus or minus 0.1.
Okay,
What?
last question.
Yes, no, it's not the last question because you're going to be asking me more, so don't lie to my face. What is it? What is your next question?
My percentage, the percentage we should do it like for the
I just told you 5 minutes ago, it's the mass. You estimate the mass from the slope and compare it to the true mass.
320.
Alright, did
Because
you write this graph down? What?
in the video you said calculate the percentage of uncertainty.
Percentage of uncertainty?
It's not the percentage that we have here of y or x. It's the
Percentage uncertainty? Yes, I'm not sure exactly what you're talking about. Are you watching the video that I did
Yeah, I
recently
watched
or for last year?
no, this was last year, but this was
Okay, well I did
something.
things a little different last year. I mean, if you want to do that, Fahad, last year I did more with the students. I decided to cut back a bit on the calculations this year. So
No, I noticed.
there's no need for you to do that percentage uncertainty. You can just give me I just want the percentage error for the math if you want a percentage, okay? Alright, did you draw this? KJ? Did you draw this?
Yes.
Right, so some vocabulary.
Vocab.
Where are you going?
I don't know, it's goal or something I'm chilling.
No food, no sleep.
No.
Yeah.
Yep.
Exactly.
You're not helping, KJ. Just be quiet and take the notes down. Elastic. That's when the material follows Hooke's law. Plastic is when the material no longer follows Hooke's law. And elastic limit is the point where the material is no longer elastic and becomes plastic. So, on our graph, the straight line part is called elastic and the curved part is called plastic. No, I'm plenty warm, thank you. I don't need the heat on. Thank you.
I don't know,
Cool.
for progressing for stuff.
Did you have breakfast?
No, it's not.
Did you have breakfast? You
No.
require energy to produce heat. You know this from physics. Energy you don't get for free. So did you get enough chemical energy this morning?
No.
No. So your potential energy is low. This is the problem.
I got some.
Did you? What did you get?
Some cereal.
Yes, sufficient chemical energy.
Yes, but I'm still cold.
Right. Yes.
I took a bath around 7, I came around 8:30, I could like see you, I was like, you came around 8:30, but they didn't know. Dennis said it, now he comes around 9.
Depends on the morning. Lately it's more around about 8:50. Okay. You got this?
Yes.
Yes. So on the graph, the first part is the elastic region and the second part is the plastic region. Okay. Right. So a little formula to arrive at. We have a mass M and it's hung. You know what? I'll just draw it. So what we have here, we have our ceiling. And we have our mass here. And it's hanging from the ceiling. And it's in equilibrium. It's balanced here. And then what happens is somebody comes along and pulls it down a distance. So imagine this is hanging from the ceiling, it's not moving, you grab it, you pull it down and you release, what happens?
Boing.
Thank you, so eloquently put. Yes, boing boing. So it'll go up and down and so on. Boing, boing indeed. Right, so let's calculate the force here. What's the force acting downwards? It's mg. And the force acting upwards, that's m delta the x. which I'm going to call the distance here is x.
Okay.
Yeah?
Why the MX?
Tis not. It's kx.
Why the KX? Okay, yes, 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 KX.
Yeah?
I know.
Now, the problem is a little bit more complicated than it looks. I have to break it up in stages because it's not actually clear what the x is. So let's go bit by bit. So firstly, you come along and you hang the elastic on the ceiling. Its length is L. Will it stay at L?
No.
No, it will droop down a bit and reach equilibrium. So it'll droop a bit and we'll call this extra piece, it's the extension, but I'll just call it for the moment. I don't want to use the same letter as X, so I don't like it, but I'll call it E. Now what's the force acting up here? The force is K times E. And what's the force acting down? mg. In this picture, they're balanced, right? So Ke equals mg. So what's do I want? The K or the E? I want the E. E equals mg over K. Now, in the next picture, look, it is pulled down by the person. So remember we said this is the equilibrium here. We're calling this distance here x. The force pulling down on it, how much is that? mg. And the force pulling up on it is k. And what's the extension?
EX. X plus E.
It will be x plus e, correct. Which is x plus mg over k. All true? May I resume? So, if I go down a bit, what is the total force acting on this? It is k x plus mg over k minus mg. Now in this picture we're calling up positive and down negative. Okay, you got that? But if you open this up, the k multiplies the mg over k, and what are you left with here? What's here? This piece will become, when you multiply by k, mg. So this actually cancels with this. So what are you left with? Kx. Which is actually what we said at the start, but we didn't know that for certain. But now we have it for certain that it's kx. So in fact, my point I'm making is, it didn't matter that it extended beyond the natural length in the last picture. Anyway, what's the formula for for force by Newton's second law? Ma. So then that means A equals m over k x, or s for position, if we call this an s. Now, the signs are a little bit messed up because this here is heading down. So which way is the force acting? Up. So in fact, there's almost like a minus sign here because this acceleration is opposite to the direction which it's moving. The acceleration is up. So if it makes it a little bit clearer, you can think about it as being like a minus sign here. Does this formula look familiar? Acceleration equals minus a constant times position. It does. What's this formula for? Simple harmonic motion, or as KJ has dubbed it, boing boing motion.
Yeah, that's very simple.
So you can get omega equals root m over k. What's the formula for periodic time? 2 pi over omega. So you now have this formula, 2 pi root k over m. That is the time required for the particle to go up and come back down. One cycle of Bunyan. This is the proof for the formula. A bit like how we did the proof for the pendulum.
That one was like G.
Yep. And this one is k over m. So, in this formula, unlike with the pendulum, the mass does matter. And of course the k matters. But what I find very interesting, if you really think about it, what's very interesting is that the g is not in the formula, is it? Therefore, this would be the same formula if this spring was on the moon. So if you imagine taking this to the moon and doing the same thing, the time would still be the same. The g does not enter the formula, meaning that the value of g is not important. Only the value of k and the value of m is. So as long as g is not 0, the time will stay the same. Does the natural length affect the time for oscillation? No. No. Okay? So, that's the formula. Now, I should point out, not only is not only you were making notes on your phone, right?
Yeah.
Note to self, look up this formula later. Not only is it true for motion like this, it's also true, of course, if it's upside down, if you have like a spring bobbing up and down, or sideways as well. You get the idea. It's basically what you might call the periodic time for a spring in motion. Okie dokie. Notice the absence of A and L, and also G. Right, let's have a look at some questions. So please write this one down. Yes? See, I told you it wasn't the last question, and I was right. So what is your next question?
If I select it means I will not.
No, don't kid me.
No, seriously.
What's your question?
The percentage of mass, I still didn't get it, okay? Till now.
Yes?
The percentage of mass
Yes?
would be the uncertainty.
No, I told you, forget about uncertainty and
Okay.
percentage, right? So what did you estimate the mass at from the slope?
I don't have like a change in mass.
What? Did you get the slope?
Yeah.
What does the slope represent?
1 over m.
Yeah. So if you do 1 over the slope, you've got the mass, don't you? Have you done that? No, why haven't you done that? That's the whole point of this assignment. So tell me what you get and compare it to the true value of the mass and get a percentage error. Yeah. Did you write the question down? What?
You said in the video one.
Oh my goodness!
No,
The
just
video.
one
Yes.
thing.
What? If you mention uncertainty.
No, I'm not
Right.
asking
Go on.
for that. I'm
Yes.
just saying that
Yes.
you, in the video you did 1 over m. You said 1 over m and the other formula for the calculating it's almost the same value. Is that right? Till now?
1 over m should be almost the same as the true mass.
Yeah.
Yes.
No, okay, tell me.
Okay. So the natural length is 10 centimeters. The extension is also 10 centimeters. So the rubber band goes from this to this. So the force is K extension which is 1 times 0.1, which is 0.1 newtons.
Okay, the K is 1 Newton.
That's what I said, isn't it? Well, you would know that if you wrote it down, like you said you did. Yes.
No, I'm not sure.
In the formula of
For what?
exercise,
Yes.
the mass will be over or the one what n results will be over.
What?
The total
What?
mass.
Just what's your total mass? You said it's 1.05.
Yeah.
Agreed?
Yeah.
Agreed. What did you estimate the mass as from your slope?
1.216.
Fine. That minus that over the 1.05 times 100. You know how to get percentage error, don't you? You did this in chemistry too, right? Right? You see, you're exhausted now and you're forgetting what you're doing. Did you do percentage error in chemistry?
Yeah.
Yeah. Everything's so blurry and hazy now, huh?
Can't remember it.
We're zooming. Okay, so let me see here. Next. Okay, write this one down. So, what happens here? You have 2 kilograms hung at the end of the spring and it extends a distance of 5 centimeters. So the force that's pulling this down is the weight, which is 2g, and the force which pulls it up is from the spring, which will be 0.05 k. And if it's not moving, it must be balanced. So you have 0.05 k equals 2g, so k equals 392.4 newtons per meter. Next question?
Yes.
No. He's thinking about the mass and percentage, aren't you?
Yeah.
What's wrong?
I asked
Yes?
in the percentage formula.
Yes?
One thing should go on the
Dude, what is
denominator
your
and the
true mass? 1.05, isn't it? And what is your estimated mass? 1.216.
216.
216. Okay, so your percentage error is 1.216 minus 1.05 over 1.05 times 100%. 1.216 minus 1.05 divided by 1.05 times 100. So like I said earlier, you got 15.8%. So I said it was about 14%. That was your percentage error.
I'm just trying to figure it out.
There's nothing to figure out. There's no figuring out here. Right, next question here. A spring constant with constant of 2 newtons per meter is attached to the wall. A boy pulled a distance of 10 centimeters. How much work was done by the boy? So what happens here is you have your spring, and the K is 2, and the boy pulls it a distance of 10 centimeters. How much work has he done? Well, you know the formula here. Work is a half kx squared. So that's a half times 2 times 0.1 squared, which is 0.01 joules. So, you know,
One point four four.
10 millijoules of work. It's fine.
Milli. So I make that a small m.
Yes. Not a big M. You didn't do 10 megajoules of work. Yeah?
Yes.
Right?
More questions?
Rubber band attached to the ceiling, a 100-gram weight is hung down on the rubber band and extends a distance of 5. The weight is pulled down a further 4 centimeters and released. How long till the rate reaches its maximum height? So what you got here? It's 100 grams. It's pulled down a distance of 4 centimeters, and then up and down it goes. Now, we don't know the K, but we are told when it's hung, it extends 5 centimeters. So originally, when you hang it on the ceiling, it will drop 5 centimeters. So you can use the trick from earlier. The weight is mg, and the force going up is kx, and they must be balanced in this picture before the boy pulls on it. So you have K 0.05 equals M, which is 0.1 times G. So you can get the K, no problem. So I got K of 19.62. So the formula is T equals 2 pi root, what is it, K over M? Was it? Or M over K?
K over m.
Are you sure?
Yes.
Alright, if you're sure. So this time you get is, no, that can't be right, 88 seconds.
That's too long.
That's a long wait. Maybe my K is wrong. No, 19.62. 88 seconds. Wow. That's ginormous. That can't be right. I must have made these numbers really badly. Anyway, it's not 88 seconds because you only want the time to go from the bottom to the top. So we don't use 88 seconds. How much do we use? Half of this to go from the bottom to the top. So the answer is 44 seconds. Do you know what? I think I made the mass too small.
Yes. It should actually be 88 seconds.
No, it is 88 seconds.
If the mass is that
Because
tiny.
my K is too big, and the reason my K is too big is either because my mass is too big or the distance is too small.
It can't be the mass being too big.
No, I'll just change it to 50 centimeters next time. I do it with intake 2 and then everything will be fine. So if I was to change it to 50, you still get a big number, 27 seconds. Right, if I change the... Is it K over M? I will go nuts if it's M over K. Is it K over M?
Is it m over k?
Do it, it's M over K.
No, you actually said k over m.
It's M over K. God,
No, when you were working it out, you said k over m. Although the omega was m over k. And you did over omega, so it's meant to change. See, check it, check it.
K over M.
Yes, exactly.
M over K.
You see?
Ah, I see. Wait, hang on, something went wrong here then in my proof.
Yes. Something did go wrong.
That's omega is m over k. No! Omega is, uh, it's not m over k here. Here's the mistake. It should have been k over m, which makes k over m here, which made m over k here. This formula here is right. Look, it is m over k. It is m over k. Right.
So I was not wrong.
Uh, yeah, we'll call it a grey area. Right, so, m over k,
Making more sense.
making more sense now. M divided by k, square root answer times pi. So then that means your time is half the answer above, so you get a much more respectable 0.22 of a second, which is much better. Much better. It was previously 0.44, I suppose. So 0.22 to go from bottom to top. Alright?
Yes.
Yes? Return to the slides. So, yeah. Okay.
No more picture again.
No more pictures?
No. Is it, are you putting some model
I'm
again?
not. I'm afraid I'm not. I'm too busy for this. Picture away. Yes, Fahad?
Oh,
I'm tired. I'm supposed to go and solve.
in video,
Yeah?
you use this formula.
Correct. This is for the uncertainty for what?
For the whatever value they have.
The uncertainty for the A? The uncertainty for that's -1, so that was previously the uncertainty for the I don't remember.
Because
But why don't you just use what I showed you in class rather than this? Because this is last year's one. And it's, yeah.
in here, in the other thing, because you know in the video,
Yeah.
you use the example for this
Yeah.
experiment.
Mhm.
It like follows the same steps,
Yeah.
and this formula turns for the RL research
Yes.
because R was there, R is equal to 1 over M.
Yeah.
So
Well, why are you using the video from last year is fine, but it's more difficult. You should be using the more recent video.
there is no this.
I uploaded the one. You know?
I watched the one day before. They uploaded one day before.
I
And
up
I'm still open. It's still open.
my channel.
Yep.
Hang on. Let me just close this here.